under number system. The collection of all the rational numbers and irrational numbers together make we call as the real numbers. The real numbers contain both the rational and irrational numbers. If you look into the decimal expansion of the rational numbers, they have only two choices. Either they could be terminating. If they are non-terminating, then they are recurring. In case it is a non-terminating and it is non-recurring, it is called as an irrational number. Let's look into some of the examples of the rational decimal expansions. If you divide 10 by 3, where the divisor is 3, the quotient becomes 3.333 and so on. This is a case where the quotient is non-terminating and it is recurring. Which is the recurring digit here? It is 3. If you look into the remainder, when you divide 10 by 3, you get 1, 1, 1 and it's so on. The remainder never becomes 0. So, if you look into the number of recurring digits in the quotient, it is always less than the divisor itself. The divisor in this case is 3. The number of recurring digits is 1, as you can very well see. Let's look into one more example, which is 7 by 8. So, if you look into the quotient, it is terminating, like it stops after 3 digits. The remainder is 640. The remainder becomes 0 after a particular number of cases. The divisor in this case is 8. And if we look into the number of repeating digits, the number of repeating digits in this particular case is 0. Next division is 1 by 7. Here, if you look into the pattern of quotient, it is non-terminating and recurring. There is a block of numbers which will get repeated one after the other. The remainder, it never becomes 0. So, in this particular case, the divisor is 7 and the number of recurring digits is 6, which is less than the divisor. Let's look into some textbook examples. Show that 0.3333 can be expressed in the form P by Q, where P and Q are integers and Q is not equal to 0. The given number is 0.3333 and so on. Let's assume that number to be equal to a variable x. So, let x is equal to 0.3333 and so on. Now, we need to multiply this x by 10 and 10 on the other side of the equation as well. So, 10x is equal to 10 into 0.3333, which gives 3.3333. Let's assume this to be equation number 1. Now, a question could arise, why should we multiply it by 10 and why not by some other number? We choose 10 because we need to identify the number of repeating digits in the given number. Since the number of the repeating digits is 1, we multiply it by 10. In the next example, if you could see, there are two numbers, that is a block of 2 digits which get repeated. In that case, you need to multiply it by 100. Coming back to example 7, we have seen that the first equation gives rise to 3.3333. Writing 3.3333 in terms of x as 3 plus x. Now, let's consider this as equation number 2. From equation 1 and equation 2, we can derive as 10x to be equal to 3 plus x, which is 0.33. Right. Now, 10x is nothing but 3 plus x. Hence, we have derived to 3.3333. Solving for x, we get 9x is equal to 3, which implies x is equal to 1 by 3. Similarly, for the next example, you can very well see that there are two numbers as a block of digits which get repeated in the given number. Considering this particular number to be equal to x, taking this as equation 1. Now, since there are two digits that are repeating, we multiply both sides of equation 1 by 100, which gives rise to 100x is equal to 127.2727 and goes on. This we consider as equation 2. This 127.2727 we need to represent in form of x. X is what? It is 1.2727. So, this 127.2727 is represented as 126 plus 1.272727. I hope you have understood why we are writing in this format. We are trying to incorporate the value of x in this particular equation number 2. So, this gives rise to 126 plus x. We have just rewritten in terms of x. Simplifying this equation, we get the value as mentioned. Exercise 1.3, we need to write the following in the decimal form and we need to say what kind of decimal expansion each one is. 36 by 100 is a case of terminating. Why? Because the remainder becomes 0. Sum number 2, 1 by 11. It is a case of non-terminating and recurring. Why? Because the remainder does never become 0. And if you look into the pattern of the quotient, there is a certain set of digits which is always getting repeated. The next sum is 4, 1 by 8. It is a case of terminating because the remainder becomes 0. 3 by 13 is an example of non-terminating and repeating if you can look into the quotient of it. 2 by 11 is also a case of non-terminating and recurring. 329 by 400 is a case of terminating. Question number 2, you know that 1.7 is equal to 0.142857 with the pattern getting repeated. Can you predict what the decimal expansions of 2 by 7, 3 by 7 and so on without actually doing the long division? If so, how? 2 by 7 is nothing but 2 times 1 by 7. 3 by 7 is nothing but 3 times 1 by 7. If we know the value of 1 by 7, just multiply it by 2, 3 and so on to get the relevant values. Hint, study the reminders while finding the value of 1 by 7 carefully. If you look into the number of repeating digits or in the block of digits which is getting repeated, it is always less than 7 for this particular case. That is what we can infer from the remainders. Sum number 3, we need to express the given decimals in the form of p by q. The first sum is 0.6 where the repeating digit is only 1 which is 6. Assume x to be equal to the given number. Since only one digit is getting repeated, you need to multiply both the sides of the equation by 10. So 10x is equal to 6.6666. Now this equation we should represent in terms of x. So this becomes 10x is equal to 6 plus 0.6666. Simplifying this particular equation, you get the value of x to be equal to 2 by 3. The next sum is 0.47 where the repeating digit is 7. If you look into the number of repeating digits, it's only one digit which is 7. Since it is only one digit, you multiply both the sides of the equation 1 by 10, giving rise to 10x to be equal to 4.7. Now this 10x you should represent in terms of x as 10x is equal to 4.3 plus 0.47 where 0.47 is nothing but the value of x. Simplifying this equation, you get the value of x to be equal to 43 by 90. 0.001 where this pattern is getting repeated. So assume this number to be equal to x. How many digits are getting repeated? There are 3 digits which are getting repeated. So you will multiply both sides of the equation by 1000. Simplifying this equation, you get the value of x to be equal to 1 by 990. Express 0.9999 in the form of p by q. Are you surprised by your answer? Following the same steps as we have discussed in the previous sums, you evaluate the value of x to be equal to 1. This value of 1 is very close to 0.9999. If it wants to be expressed in the form of p by q, you represent x by as 1 by 1. Sum number 5, what can be the maximum number of digits in the repeating block of digits in the decimal expansion of 1 by 17? If you look into the answer, there is a certain set of digits which gets repeated. So here in this case, the number of repeating digits will always be less than the divisor. In this case, it is 16. Look at several examples of rational numbers in the form P by Q, where P and Q are integers with no common factors other than 1 and having terminating decimal representations. So this is a definition of rational numbers when they can be represented in the form P by Q, where P and Q are integers and P and Q should not have any common factor other than 1, meaning P and Q are co-primes. Now if you look into the quotient of such kind of rational numbers, they can have some two categories of quotients, namely one is terminating, where the number of repeating, where the number of the remainder becomes 0 after some point in time. You call it terminating. If it is non-terminating, then there is a block of digits which gets repeated. So it is called as non-terminating but recurrent. In this particular example, they are asking only about the terminating factors. So what is the rules that are to be adhered for the terminating decimals? The terminating decimals can be represented as a fraction P by Q, where P can be represented as a power of 10. Say for example, if you consider 0.25, it is nothing but 1 by 8 and it can be represented as 125 by 1000. If you consider Q to be equal to 1000, it can be represented as a power of 10. The other rule could be the denominator rule. A simplified fraction a by b terminates if b is equal to 2 to the power of n times 5 to the power of m, where n and m are non-negative integers. Now, the prime factorization of the denominator b has the power of only 2. If it has the power of only 2, then m takes the value 0. So, the denominator can be represented in the form of 2 to the power of n. If n takes the value 0, then 2 to the power of 0 becomes 1. So, q is represented only in the format 5 to the power of m. Or the denominator q could be of the format. It can be represented as 2 to the power of n times 5 to the power of m. In both these cases, if it satisfies them, then we can say that the rational number is of the format terminating quotient. The prime factorization of the denominator of the given fractions has the power of only 2 or only 5 or both in this case. Question number 7. Write three numbers whose decimal expansions are non-terminating, non-recurring. The case of terminating or non-terminating and recurring are called rational numbers. So this is a category which is not satisfying them both the conditions. So they are irrational numbers. We need to find the irrational numbers. So some examples of irrational numbers could be pi, the value of non-perfect squares, non-perfect cubes like root 2, and so on. The square root of any prime number is an irrational number. So if you want to give an example of an irrational number, you can choose the square root of any prime numbers, which would definitely be an irrational number. Sums 8 and 9 you can very well understand from the explanation given.